We have all been there. You're back in college, you turn in a massive semester-long group project. You worked hard, but the professor grades it and gives the group a 40%, an F. Now the panic sets in, the anger sets in, and you look at your teammates. Who messed up? Was it Alice, who did the background research? Was it Bob, who wrote the backend code? Or was it Charlie, who made the PowerPoint slides? You can't just fix everyone. That doesn't solve the problem. You need to assign blame precisely so you can fix it for the next time. Maybe Alice's research was actually perfect, so her blame is 0. But Bob's code crashed during the demo. His blame is high. And Charlie? Maybe his slides were okay, but they had typos. His blame is medium. This blame game is exactly, and I mean exactly, what backpropagation is. In a neural network, you have millions, sometimes billions of neurons working together like a giant team to produce a single answer. When that answer is wrong, when the loss is high, we need a systematic way to travel backwards from the error. Pointing a finger to every single weight in the network and saying, you contributed 0.05 to this error. Change yourself. You contribute minus 0.8. You messed up big time. Backpropagation is the algorithm that calculates this blame. It is the mathematical engine that allows a computer to learn from its mistakes. Without it, we don't have ChatGPT, we don't have self-driving car, we just have random number generators. Today, we are going to conquer the math that scares everyone away from AI. We aren't just going to memorize formulas. We are going to visualize the computational graph, we are going to master the chain rule, and we are even going to cover gradient checkpointing, the secret memory-saving technique used to train massive LLMs like GPT-4. By the end of this video, you won't just run function.backward in PyTorch, you'll understand exactly what it's doing under the hood. Hey everyone, welcome back to Sumantra Codes. I'm Sumantra. If you're following our deep learning series, you know we have already built the network architecture and we have learned about loss function. But those are static pieces. Today, we learn how to make them move. Training a neural network happens in two distinct rhythmic phases. It's like breathing. Inhale and exhale. Phase 1, the forward pass or the prediction. Data flows from the left to right. Input X enter the network. It gets multiplied by weights or W, added to the biases or B, and squashed by activation function or sigma. It passes through layer 1, then layer 2, then layer 3, ... Finally, it spits out prediction y hat. We compare y hat to the actual truth y using our loss function L. This tells us how bad we did. Phase 2, the backward pass or the learning. This is where backpropagation lives. Information flows from right to left. We start with the loss, we calculate the gradient or the blame, and we pass this gradient back through every single layer all the way to the first input. Technically, computer scientists call this reverse mode automatic differentiation. That sounds terrifying, right? But don't let the fancy name scare you, as at its core, backprop is just one simple idea from high school calculus applied over and over again, the chain rule. Let's break it down. To understand backprop, you need to stop thinking in equations and start thinking in graphs. Every mathematical expression, no matter how complex, can be drawn as a circuit diagram of simple gates. Let's take a simple expression. F function of x, y, and z is equal to bracket x plus y bracket close multiplied by z. Let's pretend this is our neural network. X and y are inputs, z is a weight, f is a loss. Let's give them numbers. X is equal to minus 2, y is equal to 5, z is equal to minus 4. First, node 1 or the adder. Let's call this intermediate value q. So q is assigned x plus y. So q is equal to minus 2 plus 5 is equal to 3. Then node 2 or multiplier. Let's calculate the final output f. F is equal to q multiplied by z. So f is equal to 3 multiplied by minus 4, which is equal to minus 12. Okay, the forward pass is done. The output is minus 12. Now the magic begins, the backward pass. We want to know how does changing x, y, or z affect the final output f. Mathematically, we want to find partial derivatives df by dx, df by dy, df by dz. Step 1. The output gradient we always start at the end. How much f changes if f changes? Well, if f increases by 1, f increases by 1. The ratio is 1. So df by df is equal to 1. This is our starting signal, the seed of the backward pass. Step 2, back to node 2 or the multiplier gate. We are at the equation f is equal to q multiplied by z. We have the gradient coming from upstream, which is 1. We need to distribute it to q and z. Gradient for q is df by dq is equal to z. Why? Because the derivative of q dot z with respect to q is just the z. So the gradient is minus 4. Then gradient for z, df by dz is equal to q. Why? Because the derivatives of q dot z with respect to z is just q. So the gradient is 3. Look at what just happened. This is the multiplier gate. What did it do to the gradient? It swapped the values. The gradient flowing back to q becomes z. The gradient flowing back from z becomes q. This is a powerful intuition. In a multiplication operation, the blame on one input depends entirely on the magnitude of other input. Step 3, back to node 1 or the adder gate. We move back to q is equal to x plus y. We know that gradient coming into q is minus 4. We just calculated. How does the plus gate distribute this blame to x and y? So gradient for x is equal to df by dx is equal to df by dq multiplied by dq by dx. The derivative of x plus y with respect to x is just 1. So minus 4 into 1 is equal to minus 4. So gradient for y is the derivative with respect to y is also 1. So minus 4 into 1 is equal to minus 4. An adder gate is a gradient distributor. It takes the incoming gradient and copies it equally to all its input. It doesn't care about values of x or y. It just passes the blame along unchanged. So df by dx is equal to minus 4, df by dy is equal to minus 4, and df by dz is equal to 3. We just performed backpropagation manually. No magic, just decomposing a function into gates and flowing backward step by step. What we just did intuitively is formally known as chain rule. In calculus, if variable y depends on variable u and variable u depends on variable x, then dy by dx is equal to dy by du multiplied by du by dx. Let's translate this into deep learning speak. At any node in our computational graph, we always have two things. First, the upstream gradient, which is dl by dy, the blame coming from the layer ahead of us. This tells us how much the final loss cares about our output. And second, the local gradient, which is dy by dx. The physics of this specific gate is such as sigmoid, ReLU, or multiply function. This tells us how our output changes if our input changes locally. Backpropagation algorithm is simply downstream gradient is equal to upstream gradient into local gradient. Let's apply this to a real neuron activation. We have a forward pass y is equal to sigmoid x. So in backward, we receive a gradient from the future. Let's call it delta. We compute the local derivatives of sigmoid. Calculus tells us that derivative of sigmoid x is equal to sigmoid x multiplied by 1 minus sigmoid of x. We multiplied them. So final gradient is delta multiplied by derivative of sigmoid x. This multiplication is the chain in the chain rule. In a deep network with 100 layers, we are effectively multiplying 100 derivatives together in a long chain. So dl by dx is equal to dl by dl of 100 into dl of 100 by dl of 99 dl1 by dx. This looks elegant, right? But it hides a dark secret. A secret that almost killed deep learning in 1990s. Imagine a game of telephone. I whisper a message to the person next to me. They whisper it to the next, and so on for 100 people. If everyone whispers perfectly clearly, the message survives. But what if everyone whispers slightly quieter than the person before them? By the time the message reaches the 50th person, it's silence. It's gone. This is vanishing gradient problem. Look at the sigmoid derivative we just wrote. Sigmoid x multiplied by 1 minus sigmoid x. What is the maximum value of this number? It turns out the maximum is 0.25. Every time we pass through sigmoid layer during backprop, we multiply the gradient by at most 0.25. That means we are dividing the signal by 4. Layer 100 gradient is 1.0. Layer 99 gradient is 0.25. Layer 98 gradient is 0.0625 and so on. And finally layer 1, the gradient is 0.25 to the power of 100, which is nearly equal to 0. The signal dies. Weights in the early layers, layer 1 or layer 2, never gets the message. they never update, they never learn. The blame never reaches the people who started the project. This is why we use ReLU or rectified linear unit today. What is the derivative of ReLU? If input is greater than 0, their slope is 1. If input is less than 0, their slope is 0. Multiplying by 1 doesn't shrink the signal. 1 multiplied by 1 multiplied by 1 multiplied 1 is always equal to 1. The message survives the game of telephone. This simple change, switching from sigmoid to ReLU, is one of the main reasons deep learning works today. It keeps the chain rule from breaking. Now, you might be thinking, Sumantra, do I have to calculate these derivatives by hand every time I code? No, thank goodness. No. Framework like PyTorch and TensorFlow have an engine called AutoGrad. So when you write code in PyTorch, such as x is equal to torch.tensor with value 2 and parameter requires gradient equal to 2, y is equal to x to the exponentiation of 2, z is equal to y plus 5, PyTorch isn't calculating numbers. It is silently building the graph we drew earlier in the background. It remember, hey, z comes from y plus 5 and y came from x squared. When you type z.backward, PyTorch walks that graph in reverse. It knows the derivatives of a square is 2x. It knows the derivative of addition is 1. It multiplies them automatically and populates .grad. This is why PyTorch is called defined by run. The graph is built dynamically as you execute your code. This flexibility allows us to do crazy things in the loops and if statement inside our network, and Backprop still works perfectly. Finally, a bonus for advanced engineer. Let's talk about memory. Backprop has a cost. To calculate the gradient of sigmoid x, we need to know the x. This means we save the value of x and every other intermediate activation during the forward pass, just so we can use it later in the backward pass. For small networks, this is fine, but for model like GPT-3 with 175 billion parameters and 96 layers, storing all those intermediate activations takes terabyte of RAM. You'll get CUDA out of memory error instantly. So how do we train them? We use gradient checkpointing, also called activation recomputation. Normally, we save A, B, C, D, E in GPU memory. With checkpointing, we act selectively. We say, let's only save checkpoints, say A and C. We delete B and D to save space. But wait, when the backward pass reaches node C, it needs the value of B to calculate the gradient. But B is gone. We deleted it. What do? We pause the backward pass, we go back to the checkpoint A, we run the forward pass again from A to generate B, then we use B to compute the gradient and delete it again. The trade-off? We trade compute for memory. We agree to do about 30% more computation or recalculating those forward passes, but in exchange, we save massive amounts of VRAM. This simple trick allows us to fit giant models onto GPUs that otherwise couldn't handle them. It is the secret sauce of LLM revolution. We just survived the hardest, most mathematical topic in deep learning. Let's recap what we have learned. First, the blame game. Backpropagation is simply a method for assigning credit or blame for the error. It flows from output to input. Second, computational graph. We view equations as circuit diagrams. Adders distribute gradients equally. Multipliers swap the gradient based on input values. Third, the chain rule, the golden formula. Downstream gradient is equal to upstream gradient into local gradient. Fourth, the vanishing gradient, the telephone game problem where gradients shrink to 0. We fix this by using activations like ReLU that have a gradient of 1. Gradient checkpointing. We save memory by forgetting intermediate steps and recompute them on the fly. Next time you write the magic line lost or backward, I want you to pause. Visualize that red signal shooting backwards through your graph. Visualize it hitting the gates, multiplying derivatives, checking checkpoints, and updating weights. You aren't just writing Python code. You are conducting a symphony of calculus. If this video finally made the math click for you, if you finally understand the chain rule, hit that like button. It sends positive gradient to the YouTube algorithm to recommend this video to others. And subscribe to Sumantra Codes. Thanks for watching and keep propagating those gradients.